Good afternoon. We are here today to discuss pH basics. Your instructors for this webinar are going to be myself, Dick Yeomans of David H. Paul Incorporated, and Sherlyn Marlowe of Yokogawa. So let's get a little bit of background information on both companies. Yokogawa is a huge global network of 114 companies covering basically the entire world, 59 countries. They were founded in 1915. U.S. company is a huge company, as you can see, $4 billion a year, and they engage in cutting-edge research and innovation. They're extremely active in the industrial automation and control. We're going to put IA in parentheses, testing and measurement, aviation, and other business segments. That IA segment I mentioned earlier plays a huge vital role in a wide range of industries. Those industries include oil, chemicals, natural gas, power, iron and steel, pulp and paper, pharmaceuticals, and food. That's Yokogawa. DHP has been a world leader in high-tech water treatment training since 1989, specializing in membrane technologies, MF, UF, nanofiltration, and RO, ion exchange. We have a variety of different types of training. Online, we also do classroom and hands-on training. We can do any and all of that basically at your facility, using your equipment, training your people at the same time. Also have technical services including membrane autopsies, troubleshooting, and all types of consulting. So that's an overview of both of our companies. The two companies have come together to put together a series of 5 webinars that we're going to be putting together. First one is pH basics, then we'll move on to ORP basics. We'll talk about pH and ORP troubleshooting. We'll move on to conductivity basics, and then PLC, programmable logic controllers basics. As you can see, all of those seminars are spaced out every 2 or 3 weeks. They will all be performed on the same day each week, being Thursday, and the same time each week. Let's just say noon Mountain Time. Today we're going to concentrate on pH basics. This is the first of the series. Today's webinar is going to be about a 45-minute presentation. I'll give a real short 5, 6, 7-minute introduction. Then Sherlyn will come in and provide all the details. Then we're going to schedule it so that we can have 10 to 15 minutes of questions and answers at the end. Now during the presentation, type your questions in the question box. They will not be answered immediately. They will be addressed at the end of the presentation. So this presentation will be recorded. For future reference, it will be on our website. And at the end, in a couple of days, we will send each of you a thank you email, and you will be presented with a PDF of this presentation for future reference. So I want to make it a point that DHP and Yokogawa do not have a financial relationship. We're not endorsing their products. They're not endorsing our products or services through this webinar. This is strictly an educational opportunity that both of us are presenting to our clients to give the water treatment industry more information on what we think is a topic of interest that will give you potential value. So as far as myself, this is me, Dick Yeomans. I've been in water treatment for a long time, which means I'm getting old, I guess. I've been specializing in membrane water treatment since the late 90s, which means I've trained and consulted in hundreds of plants across the U.S. and the world. I am CWT, a certified water technologist, certified through Association of Water Technologies. I am also ROS4, Reverse Osmosis Specialist Level 4, certified through David H. Paul Incorporated. Sherlyn Marlowe is currently the Process Liquid Analyzer Product Manager for Yokogawa. She's been with them for 9 years. Her previous experience is with Bondo, better known as 3M, I guess, and Deerland Enzymes. She has a BS in biochemistry from Kennesaw State University. So those are your 2 presenters for the day. Remember that anytime during this presentation, enter your questions in the question box to the side, and at the end of the presentation, we will address as many of those questions as we can. The questions that we can't cover, they will be answered directly to you by email, and then they will be included in that recorded webinar I mentioned earlier that we will put on our website. So pH, that's what we're here to discuss today. pH, it's the hydrogen ion. That's what we're measuring. That's the acid ion, the H+1 ion. So when we call a compound an acid, what that means is that compound is giving off hydrogen ions. Weak acids, things like carbonic acid, that's the stuff in our carbonated water, or I hate to use the trade name, Coca-Colas and Pepsis and things like that. That means they give off relatively few ions, hydrogen ions. They give off very few hydrogen ions. That means we can drink them, because remember that hydrogen ion is the acid ion, as opposed to strong acids. We're familiar with hydrochloric acid. They give off a huge amount of hydrogen ions. Therefore, we can't drink them. Well, in reality, we can drink them, but we can only drink them once. Get my drift? See the little smiley face? So when we talk about pH, we're talking about that hydrogen ion concentration. We know the hydrogen ion concentration. The opposite of that is the hydroxide, or the OH, the alkaline or basic ion. At any given level of what we're going to call a pH scale, if we multiply these two together, we're always going to get a constant of 1 × 10 to the -14th. Well, let's look at this. At the highest pH level, our hydrogen ion concentration is 1 × 10 to the -14th moles per liter. Our hydroxide concentration is 1 × 10 to the 0 moles per liter. If we multiply these two together, we're going to get 1 × 10 to the -14th. When you multiply exponents, you always add them. So as the hydrogen ion concentration goes up, remember these are negative numbers, so going from -14 to -13 is going up, the hydroxide combination will go down, concentration will go down. But still, when you multiply the exponents, you're always going to get 1 × 10 to the -14th. And that continues all the way down what we're going to call a pH scale. At some point, they will become equal. We'll discuss that one again in a minute. But even continuing all the way down, if you multiply at any given level, you're always going to get 1 × 10 to the -14th. So the P in pH stands for negative logarithm. So if we put P and H together, when we talk about pH, it is the negative logarithm of the hydrogen ion concentration. So the negative logarithm we're going to express in scientific notation like this. So let's go back to our scale, remembering that pH is the measurement of the negative logarithm of the hydrogen ion concentration. And those guys in the white coat, those scientists, they did a great job of giving us a scale that we can talk about. So when I ask you what your pH is, if you say it's 1 × 10 to the -11th, you don't have to say that. You can just say it's 11. But that's what we're measuring, the negative logarithm of the hydrogen ion concentration. I mentioned it earlier. There is a point where they are equal. This is our neutral, or our 7 pH. Any pH number higher is more basic or more alkaline. Any number lower is more acidic. Now the important thing to remember about all of this is it's logarithmic. It's logarithmic over here. So a pH of 8 is 10 times more alkaline than a pH of 7. Well, a pH of 9 is 10 times more alkaline than 8 and 10 more times than 7. So a pH of 9 is 10 times 10, 100 more times alkaline than a pH of 7. It's logarithmic. So what's important about pH? Low pH can cause corrosion. High pH is corrosive also, but it can cause scale, create scaling, and particularly when we talk about CO2. So let's look at CO2 in water real quickly. Here's our pH scale. Here's our level of 100% to 0%. Well, at the lower pHs, all of the CO2 in water is in the CO2 form. But as that pH starts rising, that CO2 turns into something else. It turns into bicarbonate. But as the pH continues to go up, the bicarbonate starts decreasing, and that CO2 starts turning into carbonate. Now this really looks better when you combine all these graphs together. Here they are. There is never true 100% or a true 0%. At any level of pH, all three species exist, maybe in parts per trillion, but they're very, very low. But at the lower pHs, all the CO2 is in the CO2 form, carbon dioxide, but it's in water, so it's going to react with that water to form carbonic acid. Both of these are considered gases, but as that pH starts to go up, that CO2 starts turning into bicarbonate, and as the pH continues to go up, that bicarbonate starts turning into carbonate, which is a scaling species. Anybody ever heard of calcium carbonate? The most prevalent scale in any type of water treatment system. So that's why pH is so prevalent, so important in our water treatment schemes, especially when it comes to CO2. So I'm going to turn this over to Sherlyn, and she's going to tell us a lot more about pH.
Hi, everybody. Thank you for joining us. Let me get my PowerPoint up and running real quick. Everybody should be able to see my screen right now. Take a moment while it's kind of connecting. I'm going to show you what I'm going to talk about. He gave you the basic kind of theory behind pH. So we're going to go into that a little bit in more detail and then talk about how the actual pH electrode is physically working itself. With that, we're going to go into there. When you talk about pH, it doesn't matter whose equipment, there's all different types to consider when it comes to picking your right pH sensor as well as your reference side of your sensor. So we're going to go into what to look for so that you can go back to the process and look, this is what I'm measuring. Maybe I don't have the right stuff if you're having issues. Because if we don't have the right equipment, we've learned that our equipment actually becomes a maintenance headache for us. So we're going to go over some best practices of what we have found over the years from, us being in the field and trying and troubleshooting with customers, as well as hearing back from you guys what works from you. And I'm going to go over some calibration procedures. And then that's going to lead us into some of our question and answer section. In here, I do have a few of the most common ones, but at that point, obviously, we'll open it up to you guys as well for those questions that you have live. All right, so let's dig into the theory a little bit more. Dick said that we measure pH. One of the reasons we do it to consider for corrosion and scaling. Another reason why you may be measuring pH in your plant is because there's some applications and chemical reactions that only occur at certain pHs. So you could be using pH not just for your water quality, but for other reasons within a plant. Most common is water quality. So basically anywhere in your plant, if there's water, you're going to be measuring pH either directly or indirectly. So your cooling towers for biocide control, your wastewater treatment plant, those could be for EPA regulations. So anywhere where you have water. And for the most of the time, doesn't matter what type of plant you're in, they kind of start to go consistent throughout all the industry. So boiler feed water is boiler feed water whether you're actually at an actual power plant or you're inside utilities within a chemical plant. They're all consistent. So what is pH? Dick showed you the scale. It goes from 0 to 14. That is the textbook scale. In real life scenarios, we have seen where it can go to -2 on analyzers, all the way up to 16 on analyzers, but this is the scale. 7 is neutral. That means on the scale he showed you, the logarithmic, you have equal number of hydrogen and you have equal number of hydroxyl ions. So millivolt potential, that is what our analyzer is reading, and we'll go into that in more detail in a moment, is 0. So it's 0 millivolts. When you move downscale of that, you become what we call acidic, and when you move upscale of that, you become what we call basic alkaline. So he mentioned as well some of acids. Kind of explain that to you. Some are dangerous. Think about it like HF. If you've got HF in your plant, if you get it on your skin, you may not necessarily feel it right away, but if you don't wash your hands, if you don't clean, if you don't treat your hands right away, you can actually will eat the skin off of your hand. Whereas Coca-Cola or, you know, Pepsi, whatever, soft drinks are same thing. They've got about a pH of 2.5. They're acidic, they're very strong, because think about it, the low end of the scale is technically 0 when you look at the chemistry, you know, handbooks of it, but you can still drink it. Your stomach acid is about a 2.3, so we need that acid in our body to actually help digest food. So some acids are good, obviously some are bad. The other end of it, the basics, the caustics. Again, some of them are good, some of them are bad. Think of Drano that you may use in your house. This is a video, if you can see it as it plays, of a sponge where Drano has been poured on it that deteriorates the sponge. So obviously that's very strong, but it cleans our drains very well. Your toothpaste that you use hopefully every day, that is actually basic. It's caustic. So you can put it in your body and it doesn't hurt you as well. So either extreme doesn't mean that it's bad all the time. But again, the middle of the pH scale, if something is neither basic or acidic, we use the term neutral. These are the 3 terms you'll hear all the time. So most commonly, water. So let's look at it a little bit more detail here. Remember, he mentioned that hydroxyl ions is what we're actually measuring. Let's look at water. A rule of thumb is if you need at least about 5% of H2O in your process sample to get a true, reliable, accurate pH measurement. We get a lot of requests for jet fuel. It's a very difficult application. The sensors don't last very long. It's not very stable because there's no water in it. When you have water in there, you have equal numbers. Let's break up H2O into the hydrogen and the hydroxyl. If we have more hydrogen ions, wrong way, I'm sorry, hydrogen ions in a sample, we know that we are acidic. The reverse of it, like we've said before, if you have more hydroxyl ions, you're more basic. So what does that actually mean? In anybody's analyzer, there's a gentleman named Nurst, way long ago, that actually figured out how to calculate pH. pH is based off of the Nurst equation. We don't get into a lot of details here because it's a little too, if you don't know the mathematics, the chemistry, you can get really bored very quickly. The only thing that I want you guys to see is that T in that equation. That T stands for temperature. Temperature is one of the most important things when it comes to pH, and it has very big impact not only on the life of your equipment but also your pH measurement. So that is what I want you to get out of all of the working principles and theory behind pH, is temperature equals bad. And we'll go into more details. The other thing that I want you to get out of all this Nernst equation stuff is that when he did the calculation, he found out that 59.18 millivolts, that's what the electrode generates at room temperature at 77 degrees or 25 C, is equal to 1 whole pH shift, whether you go up or down the scale. So you're at 7 pH, you go to 6, it's equivalent to 59.16 millivolts. Other way, same thing. So those are the 2 things that we want you to know about. And the reason why we need this 59.16 millivolt in our head is when we get into maintenance, we talk about that calibration data. This can correlate to what's going on with our equipment in our actual process. So now let's look at a whole measuring circuit if you're interested in it. How does an actual pH electrode work? For ease here, we're going to keep the pH measuring and pH reference because there's 4 parts into a pH electrode itself. You have a measuring glass that's measuring the hydrogen ions. You have a reference that's creating a stable reference voltage for that potential that builds up on the sensor to be compared against. You have a temperature electrode because you have to have something to reference the temperature back to. And then you have a solution ground. Basically, you have, what we're interested in is on the measuring electrode, we want to read what potential or what the hydrogen ion activity generates, the potential differentiation it creates on this glass membrane on the measuring glass electrode. Along with that, you're going to have a glass electrode that's filled with a 7-buffer solution, and it's going to have a silver chloride pin inside of it. That's the U3 that matches the exact same silver chloride pin that's in the reference electrode. And basically the calculation that goes on in the backside of all the electronics is the sum of all of these electric potentials that are generated within a whole system. U5 is our reference junction. That's the part that's open to the process. If we have processes that contaminate that plug that should be a 0 millivolt, should create nothing and introduce anything into the, the addition of them. But if there's plugged, that will increase and you'll get errors in your pH measurement. So that's pretty much the electronics background of it. Sometimes people like to go into more details here, sometimes people don't. The only thing that's missing from this picture besides the temperature electrode that I want to mention is that solution ground. If you want to have a good, reliable, stable pH measurement, you want to make sure that you have a pH electrode that has a built-in solution ground. And there's 2 reasons for this. 2 is you need a liquid earth, and 3, if you have a system that has solution ground, it allows you to do some more diagnostics independently from on your pH glass and on your pH reference electrode. So now I mentioned that we want to measure what that potential, that U1 is shown up there, that's going on the glass membrane, right? How does it actually work? Let's think of this as compare it to a metal bar inside of a solution. The metal bar, the metal ions on this bar will dissolve slightly into the water that it's in. When it does that, some electrons are left on this metal bar, and that creates a potential difference, and that's what we're actually measuring. Look at this picture of the measuring glass electrode. Some people may realize it, some people may not, but it doesn't matter whose electrode it is. It is actually a porous glass. It means there are holes within the measuring glass electrode. Now these holes, however, are specifically designed sizes that only the hydrogen ions can fit in. So the presence of them or the lack thereof generates a millivolt. And that millivolt is what we actually measure, okay? So that's what your glass electrode, your pH glass, is actually measuring. 2 things to consider though. 1, what if you're in a caustic solution, okay? Caustic solution meaning like sodium hydroxide, for example. You still have the same measuring glass, but there's very low levels of hydrogen ions, or it's a very low acid concentration in the solution. You have, however, high sodium concentrations in your process. What happens is the sodium ions are actually bigger than the hydrogen ions, so they won't actually fit in the hole, but they actually line up along the glass electrode and kind of fakes the glass electrode to thinking that it's an acid. So you actually will read what we call sodium error in, say, about the 12 to 14 pH range. You may see this, where your equipment will read 0.17 pH off. Now, because of it thinks of it as an acid, it'll actually read low all the time. It'll read 0.17 pH low. And it doesn't matter whose equipment it is, this is still an anomaly across the board in pH measurement. It's just, however, one of the things that you have to deal with when you talk about pH is sodium errors in the caustic range, like I said, about that 2 to 14 pH range. Another thing to consider when we're looking at how this glass electrode is, they're going to be in process for a long period of time, right? They can last, some applications, they only last a week to a month. Some, they last 2, 3, 4 years. Over time, the glass layer itself will get thinner. It means you're still going to have the holes, the porousness that those hydrogen ions can fit into, but the glass sensor will erode away. Another thing that will cause erosion besides just simple, temperature or age of it is, think of it like if you've got a process that has high silica, high grainy substances in it, it'll etch it away. Those, when it etches the glass, it makes those holes that are meant to attract those hydrogen ions, to fit those hydrogen ions, not the correct size. So basically what happens is you start to get a slower response time in your pH sensor. So those are two things to consider or to think about when you're thinking about your pH system as a whole that a lot of times we skip over. Okay, now the guts. Remember how I said temperature is vital? Have you ever noticed how sometimes your temperature goes up, your pH can go down? There are two effects that temperature plays in pH samples, no matter whether it's water or not. The first one is what we call ACT, automatic temperature compensation. This is the nurse compensation. The glass electrodes, no matter whose it is, as temperature increases, expands, and as it decreases, contracts. Automatic temperature compensation is only compensating for this effect. It's just the glass, it's the nursed. However, there is another anomaly that we see, again, more on the caustic side, more if you're in about the 9 to 10, a solution temperature compensation, or a process temperature coefficient is another common term that's used. This is where you take a grab sample. Your process line is running at 180 F and it reads about 9 pH. You take a grab sample and you cool it down to 77 degrees, and now instead of 9 pH, it's reading 8.9 or 8.8. This is what we call solution temperature compensation. Most nowadays, electronics have the capability to do this added feature, but you have to manually turn it on. So ACT is what the automatic temperature compensation is doing, and let's take a look at that real quick. Most of the analyzers nowadays have a chart similar to this that are built into the backside of the electronics that it does the math. That it says, okay, I am reading a sample that is 200 degrees, and that means my differential is going to be this just because of the characteristics of the glass as it rises, as it expands and contracts, as the temperature goes up and down. This is what's on all the time, and if you want an accurate pH measurement, you need to make sure that you definitely have this feature turned on. If you're seeing another anomaly where, like I said, you're online, that process temperature coefficient, where online meter reads X, they take a grab sample and it reads Y, then you need to look at also incorporating in there the effect of like adding the extra process temperature coefficient. And you can, for the most part, calculate these very simply. You just take a grab sample, read the temperature, read the pH, let it cool, heat it up on a hot plate, do the same, and it's a simple calculation. And then you can find out what your process temperature coefficient is, go to your analyzer, turn the feature on, and then add this compensation feature in there, and then you'll have the correction automatically as well. So there's two temperature coefficients. The other thing I showed on the slide, but I didn't bring it up yet, is temperature and sensor life. Okay? If you're at room temperature and you're not in an aggressive application, you're just, plain water that doesn't have anything in it, you should be getting at least 18 years, a year to 18 years out of your life, of your probe. If you increase the temperature by 25 degrees C, you are going to shorten the life by half. So every 25 degree increase, shorten the life by half. So the higher you are, the shorter the life you are. You add to that if you're also in an aggressive application, that's also going to be a factor. But just be aware that temperature plays a vital role in the life of your probes and also the pH calculations in the electronics themselves. So right now we've only talked about the reference electrode. The glass electrode. Let's move and talk about the reference, because there's another portion of it. Remember I said there's 4 pieces. There's the glass, the reference, the solution ground, and your temperature electrode. The purpose of our reference electrode is to provide a stable millivolt value, some reference value, so that we have a 0, a background, and then any potential difference millivolt value that we read on that glass electrode, we know it's because the pH is changing. The other portion is to have a junction that's open to the process so that the two sensors can talk to each other and complete the whole continuity. Now these sensors, there are all different types of versions of them. There's different types junctions, there's different types of KCl solution, and we'll go into those in just a little bit. One thing that I want to note, though, is that that junction down there at the bottom, if that gets plugged, if we choose the wrong junction for the process, if it gets coded, that millivolt value that's supposed to be 0 that this reference probe generates is actually going to increase, which is going to show errors in our pH reading, okay? Solution ground. Why is it important? Our reference electrode is the path of least resistance when it comes into noise in our process. It's a very good conductor. So any stray currents, you have a pump that turns on, or you have plastic pipes instead of stainless steel pipes when possible. Any noise that's in our process will go directly up through our reference electrode and go into our pH analyzer and give us noisy readings. They could either be drift and drift high, drift and drift low, or just bouncing up and down. We need to make sure that we have good grounding in our system. So we need to make sure that we have a solution ground in our electrode, as well as if you do a analyzer case ground, that they're all on the same ground loop current, okay? So make sure we got proper grounding. This is one of the biggest things on a day-to-day basis that I'd say we get phone calls on, noisy readings that are just because of grounding. And there are ways to check this and troubleshoot. So we'll show you in a little bit. The other purpose of what that solution ground tells you is if you have an analyzer, and obviously because I'm Yokogawa, I put my equipment in here, so anybody's analyzer nowadays has these features, okay? So you may not be using them, but you need to look that your equipment may already have it, is you can do diagnostic information when you do your calibrations. And we're going to show you your diagnostic information and your lifetime diagnostic, because you have a solution ground and can look at the pH side and look at the reference side independently of each other. You can get on real-time indication of when that junction is starting to be plugged, when your reference electrode is starting to get coded. And that way you can go out there ahead of time before it actually just dies on you and go take care of what could possibly be an increased problem for you. So when we get into the calibration information, we'll go in how to read that, okay? So you guys should already, probably a lot of you know about these already, but we're going to take a look at what kind of sensors are out there. There's all different kinds. You have individuals, you have combinations, and you have differential electrodes nowadays, okay? What we call individual are 12 millimeter sensors. They are individual, like I showed in the pictures. You have a 12 millimeter pH glass, a 12 millimeter reference, you have a 12 millimeter sensor or temperature electrode. They all go in some holder that has a built-in solution ground. Or nowadays you have a 12 millimeter that's going into the combined. Means that in this one sensor you have a pH glass, a pH reference, a temperature, and a solution ground. Whether it's in this 12 millimeter style that's very common in food and beverage, or very common in the European market, chemical plants, or you have what we use in wastewater treatment most frequently, this wide body style is what people reference it as. It's right on, it has all of those elements built into that one body, okay? The thing to know is that there are all different types of glass formulation. Everybody's formulation is a little different, but what I want you to look at is there's most commonly two common terms used across all the time, okay? There is what we call a general purpose glass, which are normally bulb shapes, kind of like a circle at the bottom of it. These are good for non-aggressive application, your effluent, your wastewater, or your influent if you're coming from a stream or something, or a lake, those applications. If you're in aggressive applications, you want to make sure that you're choosing a glass electrode that's called a heavy duty. It means it's chemically resistant. It's normally thicker. Well, it's not normally, but it is thicker than the general purpose glass, so it's going to last longer. So if you're in an aggressive application besides chemical attack, but also particulates that are going to etch the glass, if you go with a heavy duty glass, you're going to get longer life than you would with a general purpose, okay? So there's two different types of main glass, okay? You're going to get a copy of these presentations. So these slides we're going to kind of go over a little quickly for you. That way, just put them in here so that you guys can use those for reference as well. But without looking at just what's in my process, look at your temperature as well. If you're at a higher temperature, you're really not going to want to use the general purpose glass. You're going to want to use the thicker glass if you're running at the higher temperatures as too. So we just have some reference guide charts that we put. Most common problems you're going to see with your reference, your pH glass, is you're going to see breaking. Obviously, something comes down, actually cracks the glass. It etches it, finally cracks it. You're going to see coating, aging, and temperature. Remember, higher the temperature, shorter the electrode life. Now, I told you there were all different types of junctions. So let's take a look at these real quick, okay? There's a ceramic type that is really good for general purpose applications. Then if you want to go into more aggressive applications, you're going to have a Teflon junction and then a sleeve junction for really, really dirty and ultra pure water. And what these are, these sleeve types are more what we call flowing sensors, and we use these types of sensors because there's no ions in your ultra pure water. So if you just stick a pH electrode in there, there's nothing that carries the electric current from your reference to your pH glass to make that continuity. So you have a little bit of flow that goes out that picks up that current and completes the measuring circuit. So there's different types of junction. And there's single junction, there's double junction, there's triple junction. The difference of these is obviously the process in a single junction electrode has to go through that one junction to get to the internal KCl solution before it can poison the reference pin. The double junction has to get through 2 barriers before it can attack the reference element. And then same thing, obviously, like the triple junction, it gets through 3 layers before it can actually attack the reference pin. That's just the junctions. That's just the part that's open to the process, okay? And again, more aggressive, you're probably going to have a double or triple junction. You're also going to have different KCl solutions that are internal fill. So let's look at making sure that we have the right KCl solution for our process. If we are over 80 degrees C, we're really not going to want to use a gel KCl. If we use a gel KCl, it's actually going to thin it and it's going to liquefy it. Okay. Same thing if we're below a 2 pH. If we're in aggressive acid application, process gets into our reference, it's going to actually I guess contaminate would be the correct word, the internal KCl solution, and it will turn it from a gel to a liquid. When we get the liquid, we start getting all kinds of noisy readings, and sometimes you can't go back, you can't fix it. Then we have liquid junction. This is like our liquid KCl solution. This is what I said is most commonly used in ultra pure water. We show here 3.3 because that's where a lot of the manufacturers are migrating to over the traditional 1 molar KCl. 3.3 is thicker, more concentrated, it lasts longer. If you're in an application such as brine, you're going to want to make sure you have a sensor that has more salt crystal KCl concentration. And then there's also some out there as well that have gels and combination of salt crystals in there. So obviously as you go up, you get longer life out of these. So this is just something, again, quick reference for you guys in the future. Most commonly what you're going to see in water, ultra pure water treatments, RO skids, your DI water, is you're going to have some sort of flowing reference style, or whether it's kind of like it's a sensor with a bottle that connects on top of KCl that depletes on its own just by gravity fed, or it could be a sensor that has a sidearm that this flowing one shown here on the left would be attached to a KCl reservoir tank and that has overpressure to it, and then that pumps the KCl solution into the process. Or you may have one that's more of a self-pressurizing one. These systems work in the way where there's KCl inside. The process will press up on these bellows and it forces KCl on the outside back into the process, so you don't get process ingress. These types of sensors are also good for very dirty applications because plug that junction very quickly, because if you have overpressure to the reference, the KCl, it's forcing stuff into the process, so the process can't come into the sensor and contaminate it. Another type of reference junction that you'll see out there from time to time still is what we reference as a salt bridge. It means that you have a reference electrode that isn't actually a reference electrode. It's a dummy electrode, but it has a junction, it's filled with KCl, and it's attached to a tank that has more KCl, and your true reference electrode is in there. So what happens is, like applications that have strong sulfides and stuff, they actually have to get through the dummy electrode, all the way through the tubing, all the way through the KCl reservoir tank, poison that before it can get to the reference electrode and actually poison it. So it's just another way that can actually extend the life of your sensor. Typical problems that we see with reference electrode most commonly is coding, is plugging, stray currents, and high temperatures as well. So just be aware of those. So remember we talked about temperature. I want to take a moment real quick and show you what happens with temperature in the glass electrode. Inside of most glass electrodes, there is a little air bubble that is in there, and that air bubble is meant to give room for, as temperature increases, the sensor the sensor of the process is in, the KCl in solution will expand. So that air bubble is room for that KCl to expand, okay? What it does is it ages that glass electrode a lot faster, because if it's going down, remember it's expanding it and contracting it even further. Reference electrode, what happens when you increase the temperature is that if you have a gelled KCl solution, that's going to thin it out, it's going to deplete it a lot faster. If you have a liquid, it's going to even empty out a lot faster. So the more, sometimes with sensors that are not refillable, if you have high temperatures and you have the wrong internal KCl solution, you'll deplete your reference electrode. Another thing with temperature swings is the expanding and contraction. If you go from really high temp to low temp, you'll actually have what we call pumping effect. It could suck in some of the process into your sensor, and it can contaminate your sensor. And then what happens if you have really, really high temperatures? Obviously, you're going to have shortened life. So if all possible, it's good practice to cool your samples. Okay, pressure. What happens if I have applications where my pressure swings? Okay, on the glass electrode, nothing really happens. There's no influence. But on your reference electrode, you will have big influences. This is really where we see that pumping effect, where the process is forced into the sensor because the pressure is greater on the outside of the sensor, and salts will go, or go from the higher concentration to the lower concentration. It'll suck in there into the reference electrode, and then once that process is in there, it starts to contaminate and starts to attack that reference pin. And once you have that done, it's called poisoning, and you can't normally get back from that. So just to show you two examples real quick. This is one, a picture a customer showed me, sent me of their gel-filled electrode that they couldn't figure out what happened to the gel. You see the two air bubbles there. It's now liquid. So it got depleted, it got contaminated and cooled down. Temperature as well can cause crystallization, caramelization of your internal KCl solution, and once you go back, sometimes it'll work for a period of time, but then it'll be contaminated. And then here's a picture of a bypass line. So if at all possible, sample cooler, cool it down. These are for you because I think I'm running out of time. I got a little too wordy there, I'm sorry. For you to reference when you get these PowerPoints, things to look at and things for you to make sure you have the right sensors. We gave you some quick guide. These are common terms used throughout the industry as well, okay, on where you are and what kind of sensor is best for your application. So let's talk real quick about maintenance, and then we'll get into Q&A. Everybody knows that there's a difference between calibration and maintenance, right? Sometimes calibration is done just because the sensor's not working, but in all actuality, you may not need calibration, you may just need to clean it. So we're going to go over what we suggest as the best practice. Here's just an example of electrode after 1 week. There's two ways to clean it. Obviously, manually. There's some applications where I know they have a sensor. They just go in every morning, pull it out of the tank, wipe it with a cloth, and stick it back in, and it works. That's fine. But sometimes HCl cleaner or chemical cleaning is needed as well. Our basic steps are this. You're going to rinse it with water. You're going to immerse it in your cleaning solution. If you have to use a brush, use a very soft toothbrush. Be very careful if you're going to scratch over the glass sensor, and I'm sorry, I've got the hiccups. And then we say 5 to 10% HCl. But here's a chart of some common chemicals that we've heard from end users what they use for different types of processes. I've heard anything from 409 the toilet bowl cleaner. So you guys know your processes better than we do. You're going to know what works, but these are just some examples of what we've seen that people have used. All right, so there's three different types of calibrations. There's a 2-point calibration, there's a 1-point calibration, and now common a 3-point calibration. Within that, there's automatic and there's manual. We want you to use a 2-point calibration minimum. We don't want you to do a 1-point calibration. The reason being is if you do a 1-point, you're not actually correcting for that aging of the glass electrode. So we're going to go over what we should tell you to do. Always clean your electrodes. Clean them. If you put it in a buffer solution after you have a real good clean, and our rule of thumb has always been 0.03 pH. If it's within there, it's accurate. You don't really need to recalibrate it, but if your SOP says you have to calibrate it, you got to calibrate it. But it doesn't actually need to be recalibrated. We want you to use a 4 and a 7, and I'll show you why, and we want you to be sure you give it time to stabilize. You rush through a calibration, you get inaccurate calibrations, you get inaccurate pH readings. We prefer you not to use the 9 buffers, and this is why. NIST buffers, let's go, are, when they make a true buffer, it's 4.01, 6.86, and 9.18. These are the known values of pH buffers. They add contaminants to them to get them to the 7, 9, and 10, because way back in the day with the analog meters, you couldn't actually read a 6.86. So that's why you used US technical buffers now. That's fine. Make sure, though, that whatever you're using, if you're using an automatic compensation in the analyzer, that your buffer tables are referencing the right buffer table. Otherwise, you built in an offset right off the back, okay? And we see that quite commonly. The reason why we tell you 7 is because 7 is 0 millivolts. That's what it is on the pH scale. 6 and 7 are pretty stable. They don't have a too huge of swing over temperature swing, because remember, it's sensitive to temperature. 4, 4.01, that is the most rock solid one with temperature across any of them, and it's the least amount of additives added to it. So we want you to start with a 7 and then do a 4. You can spot check after you do the 2-point with the 9 or the 10, or you can do the 3-point. The 9 or 10, the reason why we don't want you to use those is because look at the huge difference from the 9.18, how much buffer they had to add to it to get it up to a 10 pH. If you use these, you want to use it and use it right away and throw it out, because the minute you open that bottle to air, carbon dioxide seeps in and starts decreasing the pH value of your 10. So it's the least stable, just naturally, and affected by temperature, okay? So the reason why we say do a 2-point calibration, we want you to start with a 7. The yellow line here is what your probe is right now. 7 is ideal. When you do a 1-point calibration, you're now really only accurate at that 1 point that you did the calibration on. Your sensor moves up and down scale, it's no longer accurate, okay? So do the 7, compensated. This value is going to give you your 0 offset, your asymmetry potential. It's a millivolt value. Remember, Nurse said that 1 pH is 59.16 millivolts. If I see a reading of 30 millivolts, let's just round it even to 60, 30 millivolts, that means when I put my probe into a 7 buffer, it either read 7.5 or it read 6.5, and you're building in a half a pH offset right away. So at about 15 to 20 millivolts, you need to clean it again. 35, you're going to start to get sluggish. Analyzers vary. They will alarm at 60 millivolts. They'll alarm at 120 millivolts. You can bring it in if you want. But pretty much if you get to 80, 85 millivolts, you need to look at, if cleaning's not the issue, starting to replace your electrode, okay? So this gives you indication of your reference side of your system, what's going on. Is it being poisoned? Is it being plugged? Is it being depleted? The second point of your pH electrode is when you do your calibration, is compensating for your glass electrode, the aging of it. So now it takes that nonlinear line and linearizes it, and you're accurate over the whole pH range. So that's what we say to do. We say to do a 7 and a 4, and then check with a 10, or do a 3-point cal. I'm skipping through a lot of these real quick because I'm running out of time, and I'm sorry about that. I was better yesterday when I tested myself. But again, most analyzers, anywhere from 60 to 120 will alarm. 85, if your offset is that, when you put it in your 7 buffer, pay attention because you're compensating about a pH and a half in from where you actually are, and you don't really want to maintain that way. Your slope, you get that after you do that second point. Alarms will be anywhere from 80 to 70%. They start out at 100. At 85, you're going to get sluggish readings. So at about 85, you're probably going to want to pull it, okay? Most common is asked, how frequently do I need to clean and calibrate? It depends on how accurate you want and how much maintenance you want to do, and how aggressive your application is. Sometimes people can clean and they have to calibrate once a shift. If we're calibrating once a shift and it's not really an aggressive application, we need to make sure we have the right equipment in our application. Rule of thumb we normally say is if it's a non-aggressive application and you're calibrating more than once a month, we have something else that's going on. It may just be cleaning and coating if you're in a slurry. It just needs to be cleaned more frequently than calibrated more frequently. But it's really up to you. But you know, you guys can call and ask and we can give you suggestions to help you. I put this in here for you guys to reference later. If you see these problems, these are possible causes, and it goes across everybody. The biggest one that I want you to look at is that noisy response. When you get on your analyzer, there should be a pin for your reference and a solution ground. You can jumper those together, and if your analyzer is bouncing up and down, and you jumper those two in your terminal together, and your measurement locks on, it's a good indication that you don't have good grounding. That's the most common thing that we see, that we have people quick reference test for all the time. So that brings me to the Q&A sections. By my clock, it's 2:51, so sorry about that. I will open it up for questions now, or I can go through what I see as most frequently asked questions. Alrighty, so I think we got some questions here. The first question is there a benefit to a 3-point versus a 2-point calibration? It's up to individuals, to be honest. We see 3 points more frequently in pharmaceuticals, and it depends on the analyzer as well, because different manufacturers do it differently. Sometimes you will actually have 2 different slopes, one between the 4 and the 7, and then another slope between the 7 and the 4. That's okay. Other times we see where it does a 2-point calibration, you get the one slope, and then it just shifts that entire line over. So that's more like a grab sample if you do a 2-point and then a grab sample. We don't see the benefit of doing a 3-point over the 2-point. It causes normally more headaches than it does. Next question we have is, what buffers do you recommend for boiler water calibrations, 4 and 7 or 7 and 10? Again, we say do the 4, or we say do the 7 first because it's 0 millivolts, then do the 4 because it's the most stable, and then just spot check with the 10. And then that's where if you were off and you wanted to compensate to 10, you could do a 1-point, and that's essentially doing a 3-point process cal. But we just say 7 and 4 and then check. Next question is it advisable to calibrate the sensor with temperature compensation off? Absolutely not. 2 reasons, because your glass electrode, you take it out of a process that's running 80, 90 degrees Fahrenheit, and you stick it in a buffer solution that's been room temperature, or it could be even further extremes than that. If you have that temperature compensation off, you're building in errors because your sensor is not compensating for that expanding and contraction of the glass electrode. So you always need to have that ACT, the nursed one, on. Okay, next question is, what is the lowest threshold of water conductivity below which I need a specific pH probe for ultra pure water reading? Our rule of thumb is 50 microsiemens. If you're below 50 microsiemens, you need to start looking at reference electrodes that are flowing or that have pressurized internals that are meant for low conductivity. Most of the time, the pressurized reference systems some of them go down to 10 microsiemens. Some of them can go to ultra pure water, so just read the specifications for them. But rule of thumb, 50 microsiemens, anything below that, if you don't have a pressure or flowing, you're going to get errors in your reading. Or not only errors, but you'll get very short life because the process will suck out all the KCl out of that junction and shorten it, and you can't refill it. Okay, next question here is temperature compensation is set to 25 degrees during temperature variation. That is normally the most common is 25 degrees C or 77 F room temperature. That's what all of the charts and everything reference back to, so that's very common. Next question is, my process is running at 30 C, but I'm sterilizing my media at 121 C for an hour 3 times a week. What probe and what solution do you recommend? You need to make sure that you're using a heavy-duty glass, the thickened glass, and you're also going to need to make sure that you're using the salt crystals, the thicker one. Another question here is, what strength buffer solution should you store a bench meter electrode in? Again, 7 is neutral, but 4 is just as fine. When the buffer solution that they're stored in is a KCl solution is ideal. That's the most preferable. But if you need to use a 4, you can use a 4. That's what we use commonly. Ready? And what lifetime should I expect from my probe? This is a hard one to ask because I need to know more about the application. What's the temperature? What's in there? So if you're just in an effluent wastewater, you should be getting at least 18 months, 12 to 18 months out of your probe. But if you're in a CIP application that is running all the time at 130 degrees C, you're going to get very short life out of it. Alrighty, well, it looks like that was the last question for now. Hopefully, I know I skimmed through a whole bunch of stuff. Hopefully you guys found it informative. We're all here to answer questions for you. And it doesn't have to just be about Yokogawa equipment. I'm here. You'll have my contact information. I answer just generic questions as well. I have no problem with that.
Okay, thank you, Sherlyn. Very well, very good. I learned a lot about pH today. Just as a reminder, if you want more information, feel free to contact us. DHP has all kinds of classroom, hands-on, online training. We can come to your facility to do the training. And of course, we offer all types of autopsy and consulting services. So thank you for attending. We appreciate it. Please attend the upcoming 4 in this series and over the next several weeks. But please take 15-20 seconds and answer the 3 polling questions that you're about to see before you leave. Thank you very much. We will be talking to you soon. Have a good day.